Hello, I'm Alessandro Ronca. I'm a researcher at the Department of Computer Science, University of Oxford, and I'm interested in, formal languages, temporal logic, learning, applying it to reinforcement learning. And in this talk, I'm gonna talk about recurrent neural cascades, which is a subclass of recurrent neural networks. In particular, I'm interested in their expressivity. Thank you for inviting me. Very exciting. This talk is based on some recent work, in particular two papers. One paper that got recently published at AAAI, and a paper that it's a follow-up paper, which is currently under review. Hopefully, will be out soon, but it is already available on arXiv if you're interested. Okay, I'll start with an overview, so hopefully you can get the overall idea in the first 5 minutes. So I'm interested in recurrent neural cascades. Recurrent neural cascades are, roughly speaking, RNNs, so recurrent neural cascades without cyclic dependencies among recurrent neurons. So we have recurrent neurons. Clearly, they have a cyclic dependency. They depend on themselves. This is how they maintain their state. However, the rest of the architecture is acyclic. You can think of having a sequence of recurrent neurons, each neuron depending on the previous ones and not depending on the following ones. We focus on vanilla recurrent neural networks, in particular on 10H activation. And we will also focus on we have results for RNCs in general, but turned out that there is a subclass which is particularly interesting from an expressivity point of view, and this is a subclass RNC plus, where recurrent weights are positive. So weights in general are allowed to be anything, but the recurrent weight that determines the state update of each neuron is required to be positive. We get precise expressivity results for this case. Okay, so what do we mean by expressivity? We mean expressivity in terms of formal languages. We like formal languages because they provide a unifying framework where to describe the expressivity of formalisms, such as recurrent neural networks. We see recurrent neural networks as online language recognizers. That means that when we're given an input string, the network processes the input string one element at a time. And upon reading whenever it reads one of the elements of the input sequence, performs the state update, and it also provides an output. But we can say that the actual output of the network is the one that returns upon reading the last letter. So now for each string, we have one output, binary 0, 1. Essentially, the network is telling us whether it recognizes the string or not, whether it accepts the string or not. And in fact, now we can associate with each network the language recognized by the network, which is the set of string on which it returns 1. And then we can talk formally about expressivity, which is the set of languages recognized by a class of networks. I'll give you an overview of the expressivity results we got so far. They involve the following classes of languages. So here we have the class of all formal languages, and then we have some subclasses. So we have the set of regular languages, which is very well known. It's the one that can be described in terms of regular expressions and finite automata. But we're also particularly interested in a fragment of the regular languages, which are the star-free regular languages. And then we're also interested in this other set of formal languages, not necessarily regular, which is the languages that have an identity element. And we'll try to explain this one better later, but essentially an identity element is an element that can occur in the input an arbitrary number of times without affecting the output. The results we got are the following, or at least this is a summary. We have some more, but I think these ones fit nicely together. They give quite an idea of the expressivity of recurrent neural cascades, particular RNC plus, a subclass with recurrent positive weights. So we have shown that RNC+ captures the star-free regular languages, and it does not capture any other regular language, So within the regular languages, if you have a language that is not star-free, there's no way to capture this one with a recurrent neural cascade with positive recurrent weights. And this one gives us this, nice close correspondence with star-free regular languages, which we like. We also try to look beyond the regular languages, and in particular, we looked at this case of identity, and we have excluded the possibility that RNC+ captures any formal language that is not regular and has an identity element. So why are these results relevant, right? Because star-free regular languages are really important. They essentially include all the familiar temporal patterns. Whenever you talk about temporal pattern, intuitively, you probably mean a pattern like event E has happened, or event E has always happened, or event E happened after event F, and so on and so forth. This class, the star-free regular languages, are the expressivity of many formalisms, well established and well studied in computer science. We have logic, such as the transformation logic LF. We have past linear temporal logic on finite traces, monadic first-order logic on fine linear orders, star-free regular expressions from which they take their name. And then we have some classes of automata. We have a class which is called in different ways, aperiodic automata, non-counting automata, counter-free automata, and we have group-free automata. And there are fundamental results in automata theory showing that these classes of automata all have the same expressivity, and they have the expressivity of star-free regular languages. So we think that it's very interesting that RNC+ has an expressivity that matches the expressivity of all these formalisms. And we also think that this makes it a strong candidate as a model for learning temporal patterns. As a result of our work, we developed a framework to analyze recurrent neural networks. It's an interesting framework because it brings together concepts from fields which are quite different. So we have concepts from algebraic automata theory and from dynamical systems. And in this framework, the capabilities of networks are analyzed through the capabilities of single neurons. And we focus on the ability of a single neuron to capture notable semigroups and groups, which essentially describe some core functionalities. And the potential of this framework goes beyond our current results. And actually, I'll give you an idea of the kind of results that one can show by adopting this framework. Okay, this is the end of the overview. And before moving forward, I want to describe a bit better what recurrent neural cascades are. Probably it's clear to someone who knows recurrent neural networks well, but still worth defining them. Possibly we have a specific perspective on this formalism, which is useful. We see them as dynamical systems. Actually, dynamical systems in our work are useful both to describe recurrent neural networks, but also to align them with automata. Somehow, these dynamical systems for us are an overarching framework where to cast both recurrent neural networks and finite state automata. Dynamical system is essentially a tuple where we have an input domain U, we have a set of state X, and then we have a function which, given a state and an input, tells us the next function, the next state, so tells us how to update the state. And this is the key thing, right? That is, dynamical system is something that maintains a state, right? Processes the input by maintaining a state. There is an initial state, and then there's an output domain, and then there's an output function which describes how to obtain the output given the current state. So this is the syntax of a dynamical system to give an idea about how it works.
Can I ask a quick question?
Yes, absolutely.
Output is not dependent on the new input, only on the current state. Is that correct?
Right. So in this, the way I wrote it here, yes. However, this is defined Moore style, can be defined Mill style. The core of our results does not depend on this, because actually the core of our results, as you will see, is about the dynamics of the dynamical system. So it's not really about the output function. Like you can plug in then both an output function that depends just on the state, or an output function that additionally depends on the current input. Our results apply to both cases. A dynamical system works as follows. We are given an input sequence. Here is U1, U2, U3. You can think of UT as the input at time t, or you can just think of it as a string. And then we compute states. States are computed starting from an initial state, which is given, and then from the initial state and the current input. Can you hear a cat? Very sorry. That's my cat. Okay, So so the current state is computed out of the previous state and the current input as specified by the dynamics function. And then once we have computed a state, we compute the output based on the state. There are some variants where you can compute the output additionally based also on the current input. In particular, we're interested in dynamical systems with a cascade architecture. This is a specific kind of dynamical system. It is a system that has a factored state space. And so you can see the system as consisting of multiple components, each component taking care of having its own state and taking care of updating its own state. However, in the specific case of a cascade architecture, we have that the components of a dynamical system are they don't have cyclic dependencies, as shown in this diagram here. You can also see from the specification of the dynamics function, you have that the dynamics function can be broken down into n separate dynamics functions, each of them updating the ith component of the state and taking, yes?
Can I ask a quick question? Sorry, you're probably going to talk about this in the future, but this diagram really reminds me of the Krohn-Rhodes theorem, and you've mentioned semigroups. Is that a coincidence, or?
No, it's not a coincidence. It's
okay.
not a coincidence. Yeah, absolutely. Yeah.
Will you talk about this later, or is this not relevant?
I'll talk about it later. Yeah, we use the Krohn-Rhodes theorem. Yeah.
Thanks.
Yeah. So in the cascade architecture, as you see, each component takes its previous state as input, as a part of the input to the dynamics function, and it takes this input UI, which consists not just of the external input, but also of the state of the previous components and not the following ones. So each component is doesn't simply process the input, but can also take advantage of the computation that has already been performed by the previous component. So this way can compute a more powerful, more complex object than if it had to start directly from the external input. The way it works, to give you an idea, maybe it's clear, but to give you an idea how it works at a high level as a dynamical system. However, now the way the state is updated is a bit more complex. And let's go through this one step by step. So at the first step, we receive an input U1, and each component updates its state based on the external input and the state of the previous component. So if you look at X1, so X11 is the state of the first component time 1, is updated based on the external input at time 1, U1, and its initial state X1 init. However, it does not depend on the state of the following components. It does not depend on X2 init, it does not depend on X3 init. X21, the state of the second component, can depend on its previous state and on the state of the first component, right? And the third component can depend on the first and on the second. The three, the state of the three components is updated. And then once it is updated, we compute the output based on the tuple of these three components, so the global state of the system. At the next step, something similar, recursively, right? Based on the previous state, we compute the new state with each component looking only at the previous ones, in addition to the external input. And then we compute the output, and so on and so forth. So far we've talked about dynamical systems. We introduced the cascade architecture, and this is part of the characterization of a recurrent neural cascade. What's missing is the neural part, and the neural part is given as follows. We have that the way each state is updated is done in a neural way. So we multiply the previous state by weight. We receive the state of the previous components together with external input, and we process it through a function beta I that is itself a feed-forward neural network. And then we also require the output function, which looks at the state globally to return the input. We require also this one to be implemented by feed-forward neural network. If every recurring weight Wi, the one that you see explicitly there, is positive, then we obtain the subclass RNC+. Are there any questions about the, how RNCs work? Okay, so I'll move on to the expressivity results. As stated at the beginning, we have, they can be broken down, the picture we have now, the expressivity of RNC+, can be broken down into three statements. The first statement is the positive one, right? We say what they can do. And we have shown that RNC+ captures the star-free regular languages. So every regular language, every star-free regular language can be implemented by an RNC+. I'll give you a sequence of observations on which the proof is based. The first one is due in part to the Kronerod's theorem. Essentially, out of the Kronerod's theorem, which is a fundamental theory in algebraic automata theory, one could say that it started algebraic automata theory together with together with some other key results. One can show that every star-free regular language is recognized by a cascade of flip-flop semi-automata. So at this point, what a cascade is should be clear. Is the cascade defined in terms of dynamical systems? Also, automata can be cast into this formalism of dynamical systems. What's special here is what we have in each for each component of the cascade. And what we have is flip-flop semi-automata. Flip-flop semi-automata are two-state automata. Semi-automata are actually automata without the initial state and output function or set of accepting states. So it's just the transition function. We're interested only in the way they update the state. And they describe the fundamental functionality of storing and manipulating one bit of information, like the flip-flop, like in digital circuits. You can set a bit, you can reset the bit, you can do nothing, which here is called read. This, bit being 0, 1, in this case is called low or high. It's isomorphic, right? Essentially, it represents a bit. This is what gives you the core functionality of storing one bit. But to make it useful, you want to pair a core flip-flop semi-automaton with an input function, which essentially what it gives you is this function phi. Essentially what it does is when I see this input, I'm going to do a set. When I see this other input, I'm going to do a reset. And this way you obtain a more complex semi-automaton, which essentially at its core is manipulating one bit of information. So Now we start to align recurrent neural cascades to cascades of flip-flop semi-automata. I mean, the first observation is that, yes, they are indeed cascades. So if the difference is that for now each component is not a flip-flop semi-automaton, but is a small dynamical system, neural, so it updates the state based on this tanh, linear combination, input function, and so on. We can see it like, we can replace it like with a diagram like this to hide the fact that that's, how it works internally. We see that the architecture is exactly a cascade, and now we start to align them. So the question is whether we can mimic each flip-flop semi-automaton with a recurrent neuron. And we show, this is what we show, this is the core of this result. We show that core tanh neurons capture core flip-flops. We proceed by building a quite general way of proving these results, so that can be useful in the future to prove it in some other way. Essentially, we say that a neuron is a triple consisting of a set of inputs, a set of states, and a dynamics function. And then we say that it captures a flip-flop semi-automaton when it has the following shape. The set of inputs is partitioned into 3 sets, which we call vset, vreset, and vread, not surprisingly. And the set of states is partitioned into 2 sets, x high and x low. You get the idea that vset, vreset, and vread will correspond to the inputs of a flip-flop semi-automaton, and x high, x low will correspond to the state of flip-flop semi-automaton. Now, it's, the dynamics function of this tanh neuron captures a flip-flop semi-automaton, so it's essentially doing the same thing whenever it satisfies these conditions, right? Which essentially say things like, if I start from any fx vset containing x high, says whenever from any state I start, if I receive a set input, I'm gonna go to the high state. And this is exactly what happens in the flip-flop semi-automaton. This is at an abstract level. So the question is whether a recurrent tanh neuron can satisfy these conditions. And we show it can satisfy these conditions. We provide concrete, simple conditions under which it satisfies those conditions. And so in turns, it captures a flip-flop semi-automaton. The analysis is based on, of course, the function describing the dynamics function itself of the recurrent neuron, this f of x, but also the function gx, which is related to the fixed points of the dynamics function. First of all, we require weights to be positive and strictly bigger than 1. And then it is enough to choose 2 real values, a and b, with a smaller than b, such that g of a is bigger than g of b. Now, this one can seem a bit abstract, but actually they can be chosen in a simple way. I'll discuss that next slide. And by choosing these 2 points a and b, what you obtain is a state partition, as shown in the figure, and an input partition, which satisfy the conditions I described before, and so the resulting recurrent neuron captures a flip-flop semi-automaton. To give a concrete example, we can choose the weight to be 1.7, can choose b equals minus a equals 0.44. In this case, b and minus a are b and a are the stationary points of the g function. So, and this is always a valid choice. In fact, in this case, they always satisfy a smaller than b and g of a bigger than g of b. And you obtain the following state partition, input partition, where here you can also read concrete numbers. And this is a nice state and input partition, because you see, it's quite, seems quite robust, right? There's a nice space between them, so it can really easily capture a flip-flop semi-automaton. So far the discussion was about the core of the flip-flop semi-automaton. Then the whole flip-flop semi-automaton is obtained by pairing it with an input function, but an input function can be captured by a feed-forward neural network by the universal approximation theorem. So this is not a problem. Here I want to point out that the discussion, so the arguments I gave so far are really about states and the way you update states, so about the dynamics function and the transition function of the automaton. They do not involve the output function of the system, right? Overall, what we're saying is that the systems are equivalent, but we don't really talk about equivalence. We talk more about capturing the way you update the states, right? And this is valid. And it's valid because you can develop a suitable notion of homomorphism. And you can, which is essentially a mapping between two systems. So in our case, between the recurrent network and the semi-automaton. Has to satisfy certain conditions. Essentially, is tell you that, the recurrent neural cascade is mimicking the semi-automaton in the correct way. And then based on this, you can develop a notion of homomorphic representation, which is what I meant when intuitively I said capturing. And this is just about the state and the state updates, but actually has strong implications about what this overall system paired with the output function can do. And essentially you have that homomorphic representation implies equivalence, like being able to capture with an output function. And dually, if a system captures another system, then it means that there is a homomorphism between them. So I will not go into detail about this, but I think this is really nice. This is part of the framework, and it allows you to focus on important aspects of the systems. With this one, I conclude part one. These were the high-level arguments of why or how we showed that RNC plus captures cascades of flip-flops, and hence they're free regular languages. I hope that overall it is in expressivity results, but we have developed these results to be very constructive and structural, and to give a deep understanding of how a recurrent neural cascade captures a cascade of flip-flop semi-automaton. The second part is a negative result. So now that we know that we can capture stuff-free regular languages, we want to understand whether you can capture more. The first step is to look within the regular languages. And we show that there's no other regular language that is captured by RNC+. And again, I'll go through a series of high-level observations. The first one is that automata, so if you have a language that is beyond star-free, it is recognized by an automaton which has a periodic behavior, it shows a periodic behavior. Here we have an example. It is actually a quite fundamental automaton based on the cyclic group of order 3, which is also prime. It is a simple group, and the corresponding automaton in algebraic automata theory is a prime semi-automaton. But it's quite simple. What it does, say we start in state 0, and you can give input 0, and that means like it is a counter modulo 3, means adding 0, so you stay in 0. But if you give input 1, you'll do current value of the current state plus 1 modulo 3. So 0 plus 1, you'll get 1, 1 and 1, you'll get 2, and from 2 plus 1 modulo 3, you'll go back to 0. So now what you can observe here is that if you give a repeating sequence of ones as an input, the states will alternate. What you will observe is 0, 1, 2, 0, 1, 2, 0, 1, 2, and so on and so forth forever. You observe this periodic pattern with period 3. And this is a fundamental aspect of all languages beyond star-free, regular languages beyond star-free. On the other hand, we have RNC plus that we're trying to understand whether it captures this kind of languages and automata. And what we observe is that iterated tanh dynamics, so what happened if we take this tanh neural dynamics function we apply repeatedly when we're given a convergent input, such as a sequence of ones, and the weight is positive, we observe that what happens is that the sequence converges. The sequence of states we obtain, it converges. Here there's a concrete example with weight 1.7 and input 0. You see we start from 0.1 and it increases, but essentially it converges towards 0.9 and something. And this one, we proved it formally. You always have this kind of convergence for a single neuron, whenever it's given a converging sequence of inputs. Now, having proved for a single neuron, you can develop an inductive argument to say, if I have a cascade of length 1, or consisting of just one component, I know it's convergent, we proved it. But then, given that the first one is convergent, it means that the second component will receive a convergent sequence of inputs because the external input is convergent and the state it receives from the first component is convergent. So in turn, now we have that the prefix of the cascade consisting of the first two components is converging. And by induction, also length 3 and so on, like for any length. So what we have is that if you're given we have this clash between alternation like periodic behavior and convergent behavior. So if you're given a sequence of inputs such as this 111, we have an automaton like the C3, which will show a periodic pattern over its states, like 012, 012. At the same time, we have that the states of an RNC plus will form a converging sequence. Now, what we have is that in order for the RNC to capture the automaton, there must be a homomorphism, and this homomorphism must be a continuous function. And this creates a clash, as I described now. Essentially, we have that due to the fact that the homomorphism is a continuous function, and this sequence of state xt converges to x star, we have that the limit of psi xt, so the sequence of states of the automaton, because the homomorphism returns you the state of the automaton that you want to which you want to map the state of the RNC, must converge to psi x star. So it's convergent in particular. However, what we have seen is that the sequence of states of the automaton is not convergent. And this one would violate the continuity assumption. So a continuous homomorphism cannot exist, and that means that the RNC plus cannot capture a periodic automaton. And what we conclude is that RNC plus does not capture an irregular language that is not star-free. Now I have like a bit of an intermediate, like between before moving to part 3. It's some results we have, but can be seen as they're just at the beginning, so it can be seen as future work, and is what I was saying when I was saying that our framework can be used to prove results beyond the ones we have. And essentially, we think it can be used to show that cascades can capture, like one can build cascades that capture exactly fragments of the regular languages beyond star-free, but without capturing all, without jumping directly to all regular languages. To give you an idea how to go, and this is already part of the framework, you can find it in the paper. The idea is to introduce, so far we have shown that tanh recurrent neurons capture flip-flop semautomata. So according to algebraic automata theory, Cron-Rhodes theorem, and so on, to go beyond star-free, you need to be able to capture the other prime semautomata, which are based on groups, such as the semautomaton you see here, which is the one defined by C2, the cyclic group of order 2. Essentially, this is the parity semautomaton, if you want. It's the semautomaton that implements parity or counting modulo 2. So the question is, when a recurrent neuron captures one of these automata, and how to develop a neuron that can do this. Let us consider in general a group as consisting of a countable set, say just numbers from 0 to n in a binary operation. And let us consider a neuron, something like before, right? We partition the input state and the state of inputs. However, now we partition the set of inputs into n plus 1 sets and the set of states into n plus 1 sets. So one for each element of the group. And then the condition under which the recurrent neuron captures the group-like semi-automaton is quite simple. If you start from a state which belongs to the partition I and from an input that belongs to the partition J, then we must end up into a state that belongs to the partition I times J, where times is the times from the group. So the group tells us into which state we need to go. And this way we're capturing the group. We have like one instance of a kind of neuron that can capture the C2 semi-automaton. And this is a second order 10H neuron. So here, by making use of multiplication, we can capture the C2 semi-automaton, which we have shown cannot be captured by a first order 10H recurrent neuron, right? The one with sum that we've considered before. Here, the one here. And this way, one is able to capture the fragment of regular languages that is beyond star free. And it's by no means the whole set of regular languages. It is a specific set of regular languages, which is, for instance, the set which can be characterized in a number of ways. And for instance, can be characterized as the expressivity of the transformation logic LFC2. So the idea here would be to, these are useful fundamental functionalities like parity, counting modulo number. And then there are more advanced groups like alternating groups and so on, which capture permutations and other fundamental operations. And so the idea is to find ways to develop new neurons or new architectures to capture these additional functionalities. The last part is again a negative result. And this is actually in the follow-up paper. We are trying to understand, like in the previous part, we looked at regular languages. And we have identified exactly the set of regular languages that are captured by R and C++. Now we're trying to understand whether they can capture any other language. Is there any other language that can be captured by R and C++? It is a tough question. And what we were able to show so far is that they cannot capture any other formal language as long as the language contains an identity element. We think is a very general case. It's not like completely general, but we think it's very general. I'll try to give you an idea about what I mean by identity element and how we prove the result. An identity element essentially is an element that can occur in the input string without affecting the output. So if you have a certain string that is accepted by the automaton, so a certain string that is in the language, you can interleave, put how many occurrences of this element E in the string, and the string will still be accepted by the language, will still be in the language. If it was not in the language in the first place, adding this identity element an arbitrary number of times will not make the string belong to the language. In practice, this one has like more concretely, is very common. For instance, in temporal logic, one can take one of the most elementary formulas, like the one that says whether P has occurred. And in this case, the identity element is the empty set. So if we see interpretation says, so assignments to propositional variables as sets, the empty set is an identity element. Is shown in this example here. You see there are two traces, one where P has occurred, and this one is accepted by the formula, right? The formula is true in this trace. Then there's trace 1, where P has not occurred, so that formula is false in this trace. Now, if we add the empty set at the end, this is not going to affect the outcome. If we add it in the middle, it's not going to affect the outcome either. And you can think a bit about it, right? It has no effect, because what you're looking for is whether P has occurred or not. This is in temporal logic, but actually is much more general than that. One can look at functions with an arithmetic flavor, like one could say arithmetic functions. So we have an alphabet -1, 0, and +1. And we want to consider the language where the sum of the numbers in the string is positive. So for example, we are given a string of all -1, -1, -1. This one for sure will be below 0. And then we are given a string of 2 times -1 and 3 times +1. This one, the sum is +1, is positive, we accept. Now it's easy to see that the identity element in this case is 0. Adding a 0 at any point of the string is not going to affect the sum of the elements in the string. And so it is an identity element according to our definition. Essentially, we prove this lemma, which is not immediately straightforward, but it really gives a nice structural characterization of the capabilities of RNC+ in the presence of an identity element. And then the expressivity results follow from this main lemma. We show that the following: assume that we have an RNC+, and it captures a target automaton, whose language has an identity element. Then we can show that we can capture the same automaton using, instead of an RNC+, using a cascade of 3-state semi-automata. So a cascade where each component is an automaton having 3 states. This implies regularity, and this as a consequence implies regularity, but also implies some succinctness results that I will discuss in the end. To give you an idea about the proof, first of all, we observe that, we start from the fact that we have an identity element in the language. The first thing we show is that if we have an identity element in the language, it means that any automaton that recognizes it, particularly the canonical automaton, has an identity transformation. So a transformation that, so a transition that whatever state you are, when you receive this identity element as an input, you stay in the state. So we have that the target automaton we are considering has an identity transformation. And so we can forget about the language and focus about the transition function of this automaton. In the arithmetic example we've seen, it's clear that whatever state the automaton that implements this, that recognizes this language is, when the input is 0, it will stay in that state. The second observation is similar to what we've seen in the proof of the second result, is some convergence. So now we have that if we give the input, this identity element as an input repeatedly, the target automaton, since we have shown that is the identity element induces an identity transformation, we are going to have the same, it's going to stay in the same state indefinitely. At the same time, what we have shown is that, and this also is from we've seen in the previous part, is that when we give this repeating, this input, which is repeating the same element, the RNC+, the states of an RNC+ converge to a certain state X star. And we have, we are saying that the RNC captures the target automaton, so there is a homomorphism. Now, we have the following. Actually, let me go back. We have the following. So we create an equivalence relation. We say that essentially when two states are mapped, when two states of the RNC plus are mapped to the same state of the target automaton, we say that they're equivalent. And now we see that states, these converging states must be equivalent, right? They're all mapped to the same state of the automaton. So this way we obtain a set of equivalence classes. Equivalence classes corresponds to a partition of the set of states. And then actually we can, further, we can weaken this, strengthen this equivalence relation. Because we also have that if we have two equivalent states and we receive an input, and on this input, they go to two states which are not equivalent, then we have that these two states must be equivalent. And so this way we obtain a coarser partition, a coarser set of equivalence classes. And these equivalence classes, now we're moving towards using them as states of the cascade of three-state semi-automata we want to build. Essentially, we have obtained this way, through this argument, we have obtained an equivalence relation over states, but over states of the cascade as a whole. And this would be enough to argue finiteness and so regularity of the language, but we want to derive a close structural correspondence with semi-automata cascade. And so we start to look at equivalence over state prefixes. And we do something similar. We can apply the same argument, but now over state prefixes. And we say that they're equivalent if they converge over input E, they converge to the same point, which is actually a fixed point, as I'll discuss in a second. And whether their successors are equivalent. So I'll try to be brief here, but we have this analysis over the fixed points. The goal is to use these fixed points as states of the resulting cascade of semi-automata we want to build. If we look at these points to which we converge actually happen to be fixed points of the dynamics function. And if we look at the fixed point of the whole dynamics function, that is not very satisfactory. Like we obtain, okay, we can claim that overall we have an exponential number of states, but it doesn't give us a cascade as a result. So we start to look at the tuple of fixed points to which each prefix of the cascade converges. And this way we go towards deriving states for deriving states for the components of a cascade. And then we do one more step, which is to show that it's not needed to look at the whole tuple, but one can just look at the last element of this tuple, this xi star in the last equation. And then final step, I'll give you an idea next how to obtain that. This fixed point xi star can be categorized into three classes, 1, 2, 3, we call them. This categorization of the fixed point of the single component goes through an analysis of the tanh dynamics, so the dynamics function of each component. One can analyze the fixed points, and essentially you identify these two special points on the real line, P minus and P plus, and you can show that you can classify a fixed point as 1, 2, 3 based on the relative position relatively to this P minus or P plus. Overall, we show that you can use these three states as states of a component of the cascade. So you obtain a cascade of n three-state semi-automata, which captures the target automaton we started from. It implies that the expressivity of RNC plus in the presence of an identity element is the regular languages, but it also implies some interesting succinctness results. It implies that RNC plus in the presence of an identity element can only recognize languages requiring at most 3 to the n states. and can only recognize languages requiring a cascade of 3 state semi-automata having at most n components. So to conclude, in the presence of an identity element, RNC+ are not more powerful, also in terms of succinctness, not just in terms of expressivity, of cascades of 3 state semi-automata. And yeah, this concludes part 3, where we are able to exclude this set of languages, which is colored here as part. How am I doing, Lena? How am I doing on time?
You're good. You're good.
Yeah, I'm good. Okay, so I'll conclude if taking my time if there's still some time. So I would just like to summarize the result, to go through the main claims once again. We have shown 1 positive results, which is that RNC+ captures the star-free regular languages. And we have also shown 2 negative results, so trying to understand whether to precisely characterize the expressivity of RNC+. One is that within the regular languages, the star-free are the only languages that are recognized by RNC+. And the other one is a result for languages beyond regular. And we show that there's no language beyond regular, which is captured, which has an identity element, and it is captured by an RNC+. And yeah, thank you for listening.